All right, well, that's quite an introduction. Thank you, Clark. I appreciate that very much. Yeah, Clark and I worked together for a long time, and that was one of the great pleasures of my career to make a great friend like that as I did much of this field work. So the things I'm going to talk about tonight, Clark has walked many of these hills and collected some of the samples and things. So a great deal of gratitude is owed to my friend for all those times and the things that we discovered together. So in my talk, as Clark said, I'm going to split it into two pieces because I have two things that I think are interesting statewide to contrast, one across the north central part of the Cascade Range and the Columbia River Gorge in north central Oregon, the other out in southeast Oregon, out in the high desert in the sagebrush country. Rocks of roughly equivalent age in the late Miocene to Pliocene time, so we can contrast what was going on in two areas at that time. So as well as looking at the geology, one of the things I want to also reinforce tonight is that Oregon is a complex state geologically. I mean, we're out on the leading edge of North America, adjacent to the Cascadia subduction zone. It's an active tectonic setting. There's a lot going on here. And so in order to understand that unique geologic setting, Dogami's real aim is to go out and characterize that unique geology and try and understand what the state's resources and its geologic hazards are. And we accomplish that through detailed geologic mapping. But that means because of Oregon's complexity, we have to go out and do very efficient and detailed field studies, and we integrate those with all sorts of data sets that I'm going to speak to tonight, including LIDAR, which we're all familiar with now, geochemistry, age dating, petrography, structural measurements, well information, and geophysics when we have it. And by doing this approach, we come to much better geologic maps, much more accurate and much more user-friendly by the time it gets out to those stakeholders that need the information to solve problem. And this really results in fine-tuning of the geologic map units as we know them, improved surface and subsurface resolution, as well as advances in fundamental concepts of our knowledge. And so we'll discuss some of those aspects tonight as well. But to give you just a brief overview of our geologic mapping program, it's really driven by compelling societal needs, many of which you see there. In the state these days, one of the major priorities outside of natural geologic hazards like landslides is the understanding of groundwater resources. And without a 3D geologic concept within the subsurface, it's almost impossible to understand what your water resources are. But the good geologic mapping, we also need that for planning, exploration, and development of all our other mineral and energy resources. So in the map you see before you, this kind of outlines where our project areas have been statewide, things that we've published, and where we're going. And you'll see here down in Southeast Oregon, this is the Harney Basin area that we're going to discuss tonight, as well as up here in the Middle Columbia Basin, we'll focus on the Hood River area at the crest of the Cascades. So the first part of the talk is really going to look at the Harney Basin of Southeast Oregon. This is the typical landscape you see there in the photograph. Not very distinct and apparently not much there, but I think the geologic mapping we've done reveals a little bit different story in this region. So why would we focus on the Harney Basin of Southeast Oregon? This is one of the most remote parts in the state, out by the metropolis of Burns. Okay, there's not a huge population there, but there's a significant agricultural industry there, a significant ranching community. It's also the host of a number of iconic geologic features that most of us that have traveled statewide and on field trips, we'd be very familiar with these things. But because of what's going on in the Harney Basin, OWRD, the Oregon Water Resources Department, and the U.S. Geological Survey over the past several decades, they have recognized significant groundwater declines and problems arising in the area in relation to the ag and ranching community and potentially expanding other commercial applications there as well. There's really has not been a good 3D geologic data set there. A lot of the old mapping is pretty low resolution, and it's insufficient really to solve the problem that OWRD and the USGS want to accomplish there. So we have a great opportunity in looking at the geology to help the community understand and meet its water resource needs and address those water management issues and concerns, because they're not going away in the future. So we have to learn how to grapple with them. From Dogami's perspective, it's not only a great collaborative effort between OWRD and the USGS, but the public down there formed the Harney Basin Groundwater Study Advisory Committee. So involved citizenry that has been meeting on a regular basis to try and tackle this problem and tackle it in a science-based way in collaboration with both state and federal government agencies. So it's becoming a model for how to deal with significant natural resource problems in an area. So let's look a little bit at the geology of Southeast Oregon and the area that we're at. Excuse me, let me move the pictures there. So here in Southeast Oregon, this is the Harney Basin that we will talk about, the city of Burns here in the central part of the area. So we're going to look at basically this general region. The area lies south of the Blue Mountains province, which is some of the older rocks in Oregon. Paleozoic and Mesozoic accreted terrains attached to the North American continent along the Oregon-Idaho border back in Mesozoic times. To the south, the Basin Range province, south of the Brothers Fault Zone, the major tectonic boundary there. To the east, the Oahe Uplands, a series of basalts and rhyolites in the Oregon-Idaho Graben, structural areas there. And to the west, of course, the modern Pliocene to modern high cascade volcanoes and Newberry volcano near Bend. So if we look at the overall geologic picture in this high lava plains, a series of bimodal rocks, really mostly rhyolites and then primitive basalts on the other end. The rhyolites somewhat have a westward or northwestward younging age progression towards Newberry volcano. In a mirror image, we see rocks of the Yellowstone Snake River Plain trending off towards Yellowstone caldera, with rhyolites and basalts of the Columbia River basalt erupting in Southeast Oregon around 16.5 million years ago, and younging towards Yellowstone caldera, where the rocks are 2 million years old and less, for ending in major caldera forming eruptions at Yellowstone National Park. But for the focus of what we want to talk about tonight, we're going to focus on these late Miocene Harney Basin ash flow tuffs. Many of you would be familiar with these geologic units, the oldest one of which is the Divine Canyon ash flow tuff with an age of about 9.7 million years old. And on top of that, the Prater Creek ash flow tuff with an age of about 8.5 million years old. This is the type section for the Divine Canyon ash flow tuff on Highway 395 north of Burns, headed towards John Day. Just down the road to the south is the type section for the Rattlesnake ash flow tuff. It sits on top of the Prater Creek tuff, and the Rattlesnake has an age of about 7.1 million years old. At this locality in the type section, these tuffs are interbedded with one another in between tufaceous sedimentary rock sections, and then the significant ash flow tuff that covered large regions. But this is pretty significant when we talked about what the outcrops look like here and what I'm going to talk about later and how they differ. And I will note these photographs are credit of Clark Neuendorf and his mapping of this area. He's the one that actually made the geologic maps in the Divine Canyon area, along with Bob Houston. So if we look at the ash flow tuffs a little bit more in detail, this map here on the right shows the distribution of the three tuffs. The Rattlesnake tuff is the largest of the three, covering an area of about 35,000 square kilometers with an eruptive volume of 300 cubic kilometers or more, an enormous eruption covering a broad area. Then we look a little closer. The oldest Divine Canyon tuff is this area in yellow, its mapped distribution. A slightly smaller coverage area, but still significant, and eruptive volume on the order of 250 to 300 cubic kilometers. And in between that, the 8.5 million year old Prater Creek tuff, this pink area shows the distribution, probably an eruptive volume of approximately 200 cubic kilometers and covered an area of at least 10,000 square kilometers. Now, out in the field, we use distinguishing textures, crystal content, and such to identify these in our field mapping, but we also use distinguishing chemistry collected through X-ray fluorescence analysis of whole rocks as major and trace elements. And these become distinguishing characteristics to tell them apart. For instance, contents of zirconium and niobium are all useful to tell the three tuffs apart once you get chemical compositions. One of the major issues in the central part of this talk tonight is, for better part of a century, people have looked at where do these major ash flows come from, and they've identified a number of calderas marked by these circles. Probably the most prominent and best known of which is for the Rattlesnake tuff. Martin Streck proposed that it erupted from Cape Hart Lake here in the western part of the basin, based on a number of characteristics that he saw in the rock outcrops, and suggested that that center probably lies in this region. The rest of them have been hypothesized on a variety of characteristics, but no direct evidence has been presented to where these calderas might exist. So one of the big issues out here in trying to decipher caldera location is the Rattlesnake tuff. As I said, it covers 35,000 square kilometers, and it forms a blanket over almost all older rocks within the region, thus obscuring anything that we might see that would give us evidence of the history of calderas that existed prior to the Rattlesnake, and it apparently obscures its own caldera system as well. This is an example of what one of our detailed geologic maps looks like in the Burns Butte area. You can see the level of detail that we can construct by using a variety of data sets in a LiDAR base map to come up with the pink being Rattlesnake tuff and some of the older units that it's mapped with, as well as superficial deposits, colluvium, alluvial fans, landslides. So we can make a highly detailed geologic map with data obtained from our new field data, as well as collected from previously existing data sets. But we said in the beginning, we're looking at what is the 3D model to get at the groundwater resource and how that might be controlled. Well, we need more information. Well, how can we get that? Well, in the Harney Basin, we are extremely fortunate. This is the Burns Butte Quadrangle here in white, which I was just showing you the southern part of. The quadrangles and where we looked at the Divine Canyon type section for those tuffs is up here along Highway 395. These are some of the areas that I've mapped with Clark and with Bob, as well as these areas off to the east. So we're lucky here in that these points here are deep oil and gas exploration wells that were drilled from 1912 on into 1977, the deepest of which is the federal 110 well out here west of Burns, drilled almost to a depth of 7,500 feet or 7,600 feet. So an extremely deep hole, as well as some of these others. We are fortunate that as part of Dogami statute, the cuttings from these deep wells, many of them were archived and saved for future researchers to go back and look at. There's a variety of other data that goes along with these wells that's hosted on our website. Initial well logs, lithologic descriptions, all sorts of other data about the casing of the well and construction of it. So there's a wealth of data that can be obtained, but most importantly, the cuttings were available for the federal 110, which was an oil and gas exploration well, and the CTI geothermal test well drilled in 1995 was looking at the geothermal energy potential in the area around Burns, hoping to intersect a fault structure at depth. Out here at the Weed and Poteet well, there are no cuttings left for that, but detailed lithologic logs are available. And then the Fay well, some cuttings exist at depth from about 2,500 feet down, of which we've obtained data from. So a wealth of information of which we could begin to extract the 3D geology in the Burns area. So if we go in and we look a little bit, again, at some of the major issues, this is the site of the federal 110 well. This is the Rattlesnake tuff covering the surface, Rattlesnake tuff here, and Rattlesnake tuff in the surface. There are some faults here that expose some andesite flows beneath the Rattlesnake Tuff, but otherwise, the Federal 110 well, if you go out there now, you can barely recognize where the hole was drilled, let alone understand what is the geology beneath this thin cover of rocks at the surface. If we move on to the CTI well, this is what you see at the surface of the CTI well. Again, very little information at the old Hines lumber mill, blacktop pavement, and essentially over the top of alluvium in the Harney Valley. So there's not a significant amount of information to glean, but this hole went down 1,900 feet and has cuttings to it. And here's what those cuttings look like that we now have cleaned and archived in our research collections. So what we did was we went through and did a painstaking analysis, interval by interval, every 10 feet for 7,600 feet of the CTI well and 1,956 feet 1,956 feet of the CTI well and 7,600 feet of the federal well. We also selected approximately 26 intervals out of the federal well for geochemical analyses and age dating on at least one horizon. We did the same in the CTI well, 25 intervals that we selected there and ran XRF analyses on, as well as describing in detail the lithology, mineralogy, and textures of each of these intervals. Now, I should say that in the original description of the federal well, it was described as basically a monotonous intervals of generally tertiary basalt, sedimentary rocks, and some tuff. That was the original description. So if we go in and look at a little more detail at what we actually found, again, in the image here, this is the location of the federal well, this is the CTI well, this is the Wheaton Petite, and the Fay well out here. And those are represented in my detailed lithologic logs here. So if we start with the Fay well, just down here, these were the intervals that we were able to get analyses from, a large interval of lost samples. But at the top, thin interval of Rattlesnake Tuff, some trachyandesite lava flows, a missing interval, and then these are Columbia River basalt lavas, probably Steens or Picture Gorge basalt that exist in the base of the Fay well. If we go over to the Weed and Petite, no cuttings exist here, but in a way, the way that this geology was described in here, there are some apparently diagnostic intervals for one densely crystal rich tuff layers up in here that seem remarkably like they can be Divine Canyon tuff, which is remarkably crystal rich in the field, and it appears in the same similar stratigraphic position. So we can infer some of this upper stratigraphy in the Wheaton Petite. And then the lower part of that well, the descriptions look like a combination of Columbia River basalt, probably going into older Oligocene lavas and domes at depth, which are what we see at the surface just north of Burns as you drive up through Divine Canyon and come up to the summit of Divine Canyon. Well, as we get to the west into the CTI geothermal well, things changed dramatically. In the base of the CTI well, there was over 1,000 feet of monotonous crystal pore tuff that basically shared a similar textural composition all the way down, as well as chemical composition all the way down. When you get over to the federal well, that same interval is present, but 2,000 feet lower at the upper surface than it was in the CTI well. And in there, it's replaced over the top by a thick sequence greater than 2,000 feet of trachyandesite lava flows that do not correlate back to the CTI well. But chemically, if we go in here and we look at our chemical diagram, where we use this basically to fingerprint volcanic rocks that are in outcrops that are highly separated, or in wells where we cannot see their actual relationship. In here, these are the samples that correlate between the federal 110 well and the CTI well that come from this interval in the federal well, this interval in the CTI well. This is our chemical composition when looking at niobium and zirconium ratios between those analyses. They are, for all intents and purposes, identical. Also, these samples are identical in composition to the Prater Creek tuff, which is the 8.5 million year old tuff that we see at the surface north of Divine Canyon. But in Divine Canyon, recall from the image, the Prater Creek outflow tuff there was somewhere in the range of 30 to 50 feet thick. Here, this tuff is on the order of several thousand feet. But still, the chemical correlation appears to suggest a permissive stratigraphic correlation between the federal and CTI wells. So the other important piece of data is also from the 3,040-foot interval here. We also obtained an age date from that section of the well. And we will discuss that on the following slide. One of the other things, when we looked at the texture, we also looked at what is the thin section or microscope texture of these tuffaceous intervals look like. And this is one from the federal 110 well at the 3,040-foot depth, the one that we actually obtained an age date on. This is the equivalent or chemically correlative section of rock in the CTI well. They look essentially the same in texture in hand sample, and they carry some of the same hallmarks even in thin section. This is the federal 110 depth interval from 3,040 feet. It has this distinct granophyric replacement texture where alkali feldspars are being replaced by axtilytic overgrowths. That exact same granophyric replacement is also present in the CTI well. These type of granophyric textures are related to the slow cooling and crystallization of glass components in the central parts of very thick, densely welded ignimbrites. Okay, so recall the age date. So the Prater Creek outflow tuff itself, it's been dated in two places. It has an age of 8.48 and 8.41. So roughly this is the error bars that show what the ranges and possible age of the Prater Creek might be. The sample within 3,000 feet of the federal well that also is chemically identical to the Prater Creek tuff in Divine Canyon. Well, it has a high resolution argon age of 8.52 within error of the two other ages for the Prater Creek outflow. So it's age equivalent and also compositionally equivalent. And so we make the correlation that actually this is an equivalent to the Prater Creek tuff that's widely distributed around the Harney Basin. So how does this fit together? Well, if you look at it in cross section, here's the federal well here, and here's the CTI well here. The Wheaton Petite would be out here somewhere. And basically moving from the Wheaton Petite, we have our typical Harney Basin stratigraphy. And then below that, all of that basically disappears into what we believe to be Columbia River basalt. But you cross a boundary in the Harney Basin where you go into a thick section of monotonous tuff that appears to be very similar to the Prater Creek tuff. And this geochemically and texturally monotonous tuff has thicknesses greater than 1,400 feet in most places. It has this granophyric texture that's characteristic of densely welded ignimbrites. It shares the area in pink here. It shares a similar stratigraphic position and age to the Prater Creek tuff. And maybe importantly is that where the top of the section is here of this, what we assume to be Prater Creek tuff, it is 3,000 feet lower than just across the Harney Basin on the Silvies River, and it's 2,000 feet lower than where we find it in the top of the CTI well. Also with it is this cryptic sequence of tracheandesites in the top of the federal well that do not correlate into the CTI well. And there are major fault structures as well as a major ash flow unit called the Wheeler tuff that also is confined to this area, suggesting that this tracheandesite unit is confined to a deep basin, of which restricted its distribution. And the other component is in the base of the federal well. The ash flow tuff here is intruded by a variety of rhyolite dikes, tracheandesite dikes, as well as microgranites in the very lower part of the well. So there is also an intrusive complex that exists at depth there. And so these things being put together, we suggest that actually what this is a long unrecognized caldera source for the Prater Creek ash flow tuff. It is something we call the Silvies River caldera. This is the hidden caldera system that erupted that ash flow tuff at 8.5 million years ago. And so this would be the discovery of a long sought after eruptive center for one of these tuffs. One other bit of information when you start looking around at the distribution of units here. So the federal well goes down 8,000 feet and bottoms in this thick ash flow tuff. Just to the north where you see PC, these are outcrops of Prater Creek tuff, Divine Canyon tuff, which is older. And across here, these are Mesozoic, Jurassic rocks, created terrain rocks of the IZ terrain, just 10 kilometers to the north. Over here, Columbia River basalt is widely exposed as an older unit that predates the Prater Creek in this area and has thicknesses of several hundred feet. As you cross from here to here, none of those older stratigraphic units are present in the federal 110 well. It is replaced by an 8,000 foot thick section of younger units, including laterally restricted trachyandesites and a huge thick section of ash flow tuff. Units are missing that should be there unless they are explained by a large caldera structure that removed them at 8.5 million years ago and replaced them with caldera filling units related to the eruption. So moving on from that interpretation, I want to get to the other point is what is the value of this archived and readily available geoscience information? The federal well itself was a 16-inch hole drilled in 1977, went down 7,600 feet. Well, here I give you some statistics about what that hole might cost today. So if we just did a slim hole exploration, we might get to a cost of 2 of those standard regular hole wells of close to $5.8 million. If we looked at a more substantial hole, equivalent to what the federal well is, plus cuttings, we'd be on the order of exceeding probably $12 million. And costs in Oregon are generally higher, including labor, supply, support distance, safety, environmental costs, etc. There's risk and drilling problems associated with going down, so those add insurance costs and higher estimates. And according to research that I've done and experts I've talked to, we might add 20% to these costs. So it's very expensive to obtain data that was by statute retained in 1977 and 1979. Okay, to give you some perspective, our geologic mapping program has an annual budget of $320,000 to do what we do. And these funds largely come from USGS State Map Program, but also OWRD. And since 1992, we brought in $4.6 million. And this supports staff, analytical costs, field travel expense, et cetera. So in relation to the expense of the well, that would far exceed even what we've been able to obtain in funding in 30 years. So we have this essential need to preserve, archive, and make geological survey data available, okay? So we have major advances in our analytical tools. I talked about the way we use geochemistry. We use LiDAR for our geospatial mapping. And we also have modern geophysics, which helps us to advance. In the case of the federal well, we had the distinct opportunity to reevaluate all these older samples with new analytical techniques. Obviously, this led to a much improved understanding of tectonic and volcanic history of this really key area of Oregon. We also expect that in the future, computer modeling and resources are going to be enhanced for how we can process data and begin to understand it and interpret it and look at it. We can make new measurements on lithologic properties that are only available in these core and cuttings. And it's obviously a great cost-benefit way to support future efforts that's done in the next 10 years to the next 100. Obviously, we even had data back from the Dog Mountain well in 1912. So we are extending this data collection and interpretation far beyond a century. There's a long life to this information. So what's the significance of it? Well, ultimately, the Silvies River caldera is directly adjacent to what Martin Streck presumed was the Rattlesnake Tuff eruptive site at Cape Hart Lake. So this suggests the possibility of a long-lived nested caldera system in the northwest part of the Harney Basin. Discovery of where the Divine Canyon ash flow tuff came from is going to give us much resolution to this idea and ultimately how that area developed. You know, obviously we get a much better 3D picture of what's going on in the northern Harney Basin and how the dense caldera fill impermeable tuffs like that may potentially be a not so good groundwater resource or recharge area. So it significantly benefits OWRD and USGS in their modeling. It also underscores the value of organizations like Dogame and the state of Oregon being committed to collecting, archiving, and managing these descriptions of physical samples. And the key point is, without those cuttings and being retained by statute, the Silvies River caldera would never have been known, and that is a geologic discovery that would have remained unattained. Okay, I'm going to transfer there to my next talk. Clark, do you want me to take questions at this point, or do you want me to move on?
Let's move on, and then we'll have a question and answer session after your second part.
Okay, very good. Okay, so the second part here, we're going to move over to the High Cascades, north central Oregon along the Columbia River Gorge. And we're going to talk about the Hood River Graben. So this is another area that we focused a lot of our geologic mapping over the past decade. I started working in this area in 2011, mapping right around the city of Hood River, and have since expanded out from there. In this photograph, you're looking south from an aircraft, Civil Air Patrol aircraft. We're doing emergency preparedness exercises, giving us an opportunity to go up and actually obtain photographs that are useful for the research that we're doing and to prepare for natural disasters in the future. So this is looking south towards Mount Hood volcano over the city of Hood River. But just a little bit about our project in the Mid-Columbia Basin. So it's this area we call the Mid-Columbia Basin, basically stretching from John Day Dam out east, out to Cascade Locks on the west along the Columbia River, and then south past Dufur to Ty Valley. So it's a watershed that we're looking at in support of water resources, trying to understand groundwater potential and aquifer storage and stream connectivity in this region. So our mapping goals really, if we focus in on the Hood River area along the Cascades and also the Mid-Columbia Basin, we're really looking at what is the flow-by-flow geologic contacts and what is the volcanic stratigraphy of Columbia basalt units into younger Cascade units. A big part of this is delineating faults and fault zones, as well as superficial geologic mapping to understand geologic hazards, including landslides and stream flood deposits and such. And then we're also interested in what is the structure on top of the Columbia River basalt. And then ultimately what we're going to talk about here, what is the timing and origin of the so-called Hood River Graben? So the question is, how do we get about doing this in a place like the Cascades? Well, the thing I want to reinforce here to follow up on the importance data is that this is one map they called the Dog River Quadrangle and a little piece of the Badger Lake Quadrangle on the east flank of Mount Hood volcano. Well, what you see here, all these dots are field stations on the places that we have visited and recorded notes, collected samples, or taken some sort of data to better understand the geology there. So what you see in the picture equates to 2,200 field stations, over 1,000 rock samples, greater than 800 compiled and new XRF geochemical analyses, 40 plus age dates, including new argon isotopic ages, thin section analysis of 100 thin sections, many measurements of magnetization, and then we have an operation through LiDAR that we've developed where we can collect strikes and dips or orientation, structural orientation measurements automatically based on what we see in the LiDAR. So enormous data sets that are collected then to make a geologic map that ultimately looks like that and adds significant detail to what we did not know before. So in this area, that kind of data density is absolutely necessary to understand the geologic problem. So a little bit about the geology of this region. We're looking at the High Cascades IntraArc Graben, and that is shown in this red box in this figure here. It's basically 150 kilometer long by 30 kilometer wide segmented and discontinuous intra-arc graben along the crest of the High Cascades volcanic arc. Its major offset is along eastern boundary faults. So here at Green Ridge in the south, continuing northward up into the Hood River Fault along the Hood River Valley. There's also this north younging of low potassium tholeiitic lavas, very primitive basaltic lava flows that are older in the south and get younger in the north. And so the segments basically have ages of 8 to 5 million years old in the south at Three Sisters volcano, Mount Jefferson volcano about 6 to 4 million years old, and in the Hood River Graben, 4 to 2 million years old. And then across the river in the Indian Heaven volcanic field up here in the proximity of Mount Adams, volcanic rocks less than 1 million years old. And so this IntraArc Rift is characterized by a number of Pliocene to Holocene volcanoes, as well as Pliocene to Holocene faults. So overall, where does the IntraArc Graben sit within the geologic story of Oregon? Well, it's inboard of the Cascadia subduction zone in the Juan de Fuca plate, which is obliquely subducting beneath North America. Within the North American continent and Oregon, we're getting clockwise rotation of most of the state of Oregon around a piercing point out in northeast Oregon. So the entire state is rotating as the Cascadia or Juan de Fuca plate subducts beneath North America. Locally, what do we get? We get basin and range extension to the south of the Harney Basin area. We get intra-arc extension along the Cascade crest, and we also get north-south compression in the Yakima Fold Belt across south-central Washington and north-central Oregon. So we get a very complex environment through the area that we're talking about of north-south shortening, oblique shortening, and then extension through the High Cascade crest. Okay, general geologic units in the area that we're going to talk about. I mentioned the Columbia River basalt. This is the extensive area here in pink. These lava flows were erupted in southeast Washington, northeast Oregon, and Idaho around 16 million years ago, and then traversed the central or ancestral Cascades in the Trans-Columbia Arc lowland at 16.5 million years ago to 15 million years ago across the ancestral Cascades. Over the top of those is a broad alluvial volcaniclastic plain known as the Deschutes Formation that erupted from volcanoes probably in the proximity of modern day Mount Hood, spread eastward into the Dalles area as a large volcaniclastic plain, arc adjacent plain between 8 and 5 million years ago. On top of that are lavas of the late High Cascades, and we'll talk about those a little bit. These are Pliocene and younger lavas that are associated with younger structural development of the Mount Hood to Columbia River area in the Hood River Graben. So the Hood River Graben, this is the northern segment of the High Cascades Arc Rift. It's approximately 50 kilometers long from Mount Hood up to the Columbia River, 20 to 25 kilometers wide. The major offset is along the eastern boundary fault that we call the Hood River Fault Zone. The western boundary is the newly discovered Mount Hood Fault Zone, which has been recognized from LiDAR obtained from 2007 to present, recognizing many of the little lineaments and scarps that are within this active fault zone. Formation of the Hood River Graben was largely after 3.7 million years ago, and we'll talk about that in a bit. And Holocene faulting exists on the Mount Hood fault zone, particularly down here in the Gate Creek area. And the formation of this graben is associated with these low potassium tholeite primitive basaltic lavas erupted between 4.1 and 2.5 million years ago. And just for reference, here's kind of an older view of what across the Cascade Arc, this from O'Connor and Burns, but adapted from earlier work by Allen, showing roughly the uplift of the Cascades and Columbia River basalt and the Hood River graben dropping down. And then as you go east to the Dalles and the Yakima Fold Belt, an early conceptual idea of what this area looked like. Okay, so again, our aerial photograph looking down south towards Mount Hood through the Hood River Valley, Hood River graben, with just some major features denoted on here. As I said, this occurs in an area of extension along the arc, but also in an area of compression in the Yakima Fold Belt. So you get this unique interplay of these are fold axes in the Yakima Fold Belt. These are thrust faults related to segmentation of anticlines in the Fold Belt. And then they're offset by younger extensional features, and they may in fact interplay with older, the extensional features may interplay with the compressional features, but these are lineaments of the Hood River Fault Zone extending south towards Mount Hood. This is Hood River Mountain in the prominent eastern escarpment of the Graven and the downdropped basin, and then rising up with these low potassium tholeite lavas rising up to the west towards Mount Defiance. So if we begin to go from north to south in the Graben, this is what ends up from geologic mapping, looking at my cross sections across certain areas. So in the northern Hood River Valley, these are sections of Columbia River basalt forming Hood River Mountain that we have then correlated geochemically to flows that are exposed down here in the fruit orchards on the valley floor. Here's the basalt of ginkgo down here, and then it is back up the hill here, roughly 300 meters lower than it should be. So across the Hood River Fault Zone. And we can see that in cross section. Here is that orange ginkgo layer across this part of the valley, offset across a fold axis in the Columbia River basalt, and then down dropped into the valley floor here. Younger Pliocene lavas and rocks of the Deschutes Formation in angular unconformity over older Columbia River basalt. So this is that major fault zone of where the graben is being dropped down in the east. If we move a little further south, this is in the vicinity of Parkdale. Again, the Hood River Fault runs along the prominent escarpment here. This is the Yakima Fold Belt thrust, and we also have kind of north-northwest trending strike slip faults related to the Yakima Fold Belt compressional deformation that are cutting up into the footwall of the Hood River Fault Zone. And then where I'm standing here, basically just below me are lavas of the Columbia River basalt, probably 100 feet or less in the subsurface. The upper part of that surface is now almost 1,200 feet or 1,200 meters, excuse me, above me in elevation. So the relative offset across this part of the graben is probably on the offset of 1,200 meters or 1.2 kilometers. Very significant offset. So just to give you a little example, we'll look at the cross section in a second, but this was the existing mapping that was available to solve groundwater issues or to understand structural geology or fault mechanics in the area. This was an earlier map done by the USGS in the late 80s and 90s as a 100,000 scale map, and it fit the purpose of the mapping at the time and answered many questions that needed to be answered. But significant improvements can be made on all research and geologic maps. And so that's what we attempted to tackle. So if we look at the exact area, that's what our new geologic map looks like, adding significant details to the area, as well as a number of queried fault structures, new thrust faults that have to be there, and a number of other faults that break up the Columbia River basalt stratigraphy. We've also mapped flow by flow in the Columbia River basalt so that we can find exactly how much offset there is between individual flow units. Okay, so then if we look at the cross section there, we are in that earlier photograph, I was standing about here looking up at this rim. And across several strands of the Hood River Fault Zone, we've taken this flow and dropped it down, dropped it down, dropped it down into the valley for an equivalent total cumulative offset of about 1,200 meters across this part of the Hood River Graben, creating a significant valley. Okay, we move south just a little bit more. So this photograph is for 2 points. One, to show you the a relationship from the first few slides I showed you of how much data needed to be collected. So that data was collected over this part of Mount Hood. So essentially we have walked and sampled most of this to figure out the fault arrangement and also flow stratigraphy in here. Very difficult terrain to work in. It's all on foot, but it's absolutely necessary to understand the problem at hand and what the earliest development of Mount Hood volcano is. And so these are some of the fault structures we've identified. These are north-northwest trending oblique strike slip faults, probably related to early Yakima fold belt deformation. They are offset and intersected by strands of the Hood River Fault Zone from Pliocene and later Graben development. But again, there's probably a unique interplay between these faults remaining active and activity on the Hood River Fault Zone. This is a thrust fault that we recognize that brings late Miocene dalles up. And then all of this area is filled in by lava flows of 500,000 years or less of Mount Hood. So modern Mount Hood is essentially filling in the Hood River Graben after 500,000 years ago. Okay, another example of a map in that same area. So this is the same USGS map at 100,000 scale. Again, you see the general detail you get. It's very good at what it was attempting to show at that time, but there's only a few data points here shown in black. More recent mapping, this is what we get, a detailed stratigraphy not only of the younger Mount Hood volcanics and lava flows, but a detailed stratigraphy of the Pliocene and older rocks that are structurally dismembered along these north-northwest striking strike slip faults, as well as the Hood River Fault Zone, which projects through this area. So we get significant more detail and control on what these fault strands and fault relationships actually are doing. So again, in the cross section here, we can see similar story to from south to north. These are older Dalles units that have been offset and are dropping down into the basin. Of note here is this orange lava flow layer here, which we have dated at 3.7 million years old, but out in the area around Dufur, east of the Hood River Graben. But here that same lava flow, chemically identical, and it also sits within the same age time stratigraphic framework because of other age dates we have in here. It sits deep within the Graben and is an important data point telling the story of the Graben. Okay, so we're going to take a little bit different view here of just some general mapping on Google Earth image. So we were just right down here in the Hood River Graben looking at that lava flow dated at 3.7 million years old. It is also present coming down the 5 Mile Creek drainage out towards Dufur. Equivalent rocks of similar composition, trachyandesite composition, and of same age also extend down the Pine Creek drainage well past Dufur. So there's this event at 3.7 million years ago that erupted in the area of the Hood River Graben, and it had connection to stream drainages and emptied out down the older alluvial plain that had formed on top of the Dalles Formation. Subsequently, rifting and down dropping of the Hood River Graben cut off all the headward area, source areas for those lava flows to get out, and no younger flows exited the Hood River Graben this way. They all fill in the main Graben structure. So this flow being cut off at 3.7 essentially dates the timing of onset of the Hood River Graben. As well to the north, these are 3 million year old lava flows that erupted on the top of the Graben margin and then are offset within the basin also to the east, or to the west, excuse me. And so what we see is actually an age progression from south to north of rifting or Graben formation beginning about 3.7 million years ago and progressing younging to the north past Hood River at 3, and then younging north into the Indian Heaven volcanic field. Similarly, we look at a kind of a north to south image of the same map patterns. These are these LKT or low potassium tholeite lavas on top of Hood River Mountain. And then again, in a westward dipping section offset by the Hood River Fault Zone. Age dates, Argon age dates from here are 3.05 and precisely dating the upper extent of fault offset in here. And then we'll talk in a little bit the western margin of the Hood River Graben here along the Mount Hood Fault Zone. Okay, so that's where we're going next. Here's Mount Hood in the south, north-northwest trending faults up to the Columbia River, the Gate Creek Fault segment. So these Mount Hood Fault Zone, 3 fault segments along the western Graben margin, the Gate Creek segments in red, the Blue Ridge segment in blue, and the Multipore Mountain segment in purple. This is what an oblique view of it looks like it from the Columbia River going southeast towards Mount Hood and under modern Mount Hood volcano and extending off to the southeast. Here's the basic trace of the Hood River Fault Zone on the eastern Graben margin. This is detailed mapping by Scott Bennett of the U.S. Geological Survey that shows some of the offset in the western part of the Hood River Graben, the Gate Creek Fault Zone. Of note here is this QTBR green unit. These are the Pliocene LKT lavas that date about 3 million years old in here, and they have significant offset of about 200 meters. Offset on the lower Columbia River basalt is also about 200 meters. So most of the offset on the Gate Creek Fault has been in late Pliocene to post-Pliocene time, similar to the Hood River Fault Zone and development of the rest of the Hood River Graben. There's also a right lateral oblique strike slip component to this, coincident with structures in the Yakima Fold Belt. So if we look at it from west to east, the Gate Creek Fault would exist out here as the western Graben margin, dropping the west down, and then the Hood River Fault Zone and cross section we saw earlier, dropping the eastern margin down, and the Hood River Graben in between being filled by younger post-Columbia River basalt lava flows. But similar separations of 100 to 250 meters on the west, and somewhere on 300 to 500 meters of vertical separation along the Hood River Fault Zone on the east. Okay, so getting into the last few slides to wrap up the story, this is a view looking south past the Hood River Graben down to Green Ridge and Mount Jefferson. This is where the Deschutes Formation is. We went on this on a GSOC field trip a number of years ago, and we looked at these rocks. The Deschutes Formation is a formation roughly between 8 and 5 million years old, and it's equivalent in age to the Dalles Formation. Also in the Deschutes Formation are some of these LKT lavas, but they're 8 to 5 million years old in the Deschutes Formation. Those lavas are not present in the Dalles Formation, but they are present in younger rocks as late Pliocene. So if we look at all this detailed chemistry we've collected, here is some of the takeaway, is that the Deschutes Formation lavas, here are those primitive LKT lavas erupted between 5 and 8 million years ago in the Deschutes Formation. Those similar composition lavas exist in the Hood River Graben, so the northern segment of the High Cascades Arc, but they range in age from 3 to 3.6 million years old. The Dalles Formation, which is equivalent in age to the Deschutes, is much different in composition. Now, the missing part of this diagram is that the Deschutes has a series of rhyolite ash flow tuffs and domes that formed with it, as do in the Hood River Graben. These basalts also formed with rhyolites and ash flow tuff as well. So we're beginning to understand the types of rocks that are present, and also validating an idea that was brought forth by Rick Connery that the High Cascades Rift actually propagated from north to or south to north between 8 and 2 million years ago, with the Hood River Graben being the youngest part of the rift, or the propagating tip of the rift. The other general part is that if you collect enough data, you begin to see the different eruptive episodes, whether it's Dalles Formation or Mount Hood volcano or Pliocene volcanics. They begin to separate out into distinct groups that then future petrogenic analyses can be done to really understand what was sourcing all of these different volcanic episodes tying to structural events. So kind of to wrap things up in conclusion here, what have we learned? Well, the Hood River Graben is part of the Interarc High Cascades Graben, but it occurs in a step over in oblique right lateral structures that cross the arc at high angles. So here are these north-northwest trending structures that cross the Cascade Arc, and the Hood River Graben forms two rhombohedral segments essentially between two strike slip zones. And so basically in a stress field of clockwise rotation, you end up with pull apart rifts in the northern part of the Cascade Arc between basically two major master faults, north-northwest striking master faults. The question is, why has the style of deformation recently changed in the Hood River area from compression to this arc-related extension, then to arc-related extension with strike slip movement? And so the idea is that Yakima folding gave way to northwest trending transtension, so basically extension within strike slip fault zones at 3 to 4 MA with the arrival of the LKT volcanism and as the High Cascades Graben propagated northward. And so it would look something like this, is that as those primitive lavas are erupted northward as they propagate northward, you basically are enhancing intra-arc rifting between the northwest striking right lateral faults of the Yakima fold belt. And so the Hood River Graben is basically a transtensional pull-apart basin between the strike slip fault zones. And that also explains a major missing feature is we've always had the question is, why does the Green Ridge fault zone not connect up north to the Hood River fault zone? And this explains why, as major north-northwest striking fault zones extend and segment the arc, such as the Sisters Brothers fault zone and what we call the Dog River Badger Lake fault zones and Gales Creek fault zones in the Portland area. The arc is basically segmented and the intra-arc graben is forming in between those. Okay, and so this is what these strike slip pull apart basins would look like. So basically the Hood River Graben is basically formed as a transtensional pull apart basin. It's not simply an east to west extensional graben that's being filled in. But within the High Cascades, there is this time transgressive nature from south to north, chiefly post 3.7 million years old on the south in Hood River Graben, and then post 3 million years old in the north, and it's associated with these primitive LKT lavas. And so, you know, just to conclude here, all of that research was supported by the USGS State Map program. There's all the grant numbers for better than 10 years, a decade of work in here and in the Harney Basin. And of course, we significantly acknowledge that many of these funds came also from the state of Oregon through Dogami and the Oregon Water Resources Department. So without this interest in funding geologic research, none of this would have been possible. So I really appreciate the opportunity to talk to GSOC and hope to do it in person again soon, Sheila.
Hey, that was awesome. Very good. Let's get some questions. I know there's lots of questions.
I'll do my best.
I had one and you answered it already, so.
So Jason, is it your preference to pick out the questions yourself in the chat, or would you like me to read them to you?
Well, let's see. Maybe I can stop sharing and then I could figure, well, I can see the chat. Let's see.
I'm happy to read them if you'd like. Your preference.
Well, why don't you go ahead and read them? I'll get lost in the chat. So yeah, if you would, please.
Yeah. So, well, Sheila started out making a comment that your maps and cross sections would make William Smith proud. So. Oh, wow. That is, that's beyond high praise there, Sheila. Thank you for that. And Paul kind of made a general comment earlier on about, you know, are there ways that GSOC can support? I don't know if you have any thoughts on that. You broke up a little bit, but I think the question was, how can GSOC support Dogami? Correct. Yeah.
Well, I think it was really critical during the last legislative sessions and some of the downturn that the agency had overwhelming public support for geologic research in general. And I mean, you mentioned the energy hub bill and things coming up and all these critical infrastructure things that we work on. So I think just continuing to stay engaged in what's going on and staying engaged in how things develop within leadership within the state is probably the most important, and then plugging in where you find opportunities, because certainly we found that Dogami has enormous support from our stakeholders and is critically important to continue to get the message out there. So I would say continue to keep putting on presentations where you bring in people and making geosciences readily available to the public is great.
All right. Patty asked on your first presentation, how is the Silvies caldera information related to groundwater in Burns Basin?
Yeah, so that's a good question. I didn't have a lot of time to touch on that, but the idea in some of these areas, so the USGS has come in a major project over northern Nevada and southeast Oregon, looking at the Northwest Volcanic Aquifer study, basically a large study they're looking at. In that study, they basically have generalized a lot of volcanic geologic units that make a broad overview of what water resources might be over a large area. But as we zoom in a little bit, the question is, in the Harney Basin, which units actually host groundwater and where is that recharge of groundwater coming from? And in lots of areas of Oregon, that model is these Columbia River basalt flows, and the intervening layers between individual flows are the host aquifers. And since the Columbia River basalt is present in the Harney Basin, that is one logical area that if you went deeper in there, you could potentially tap Columbia River basalt type aquifers. What this work does is basically makes that entire northwest part of the Harney Basin probably a very low potential recharge area and low potential storage area. Essentially, none of those layered basalt flows or rocks that would have intervening layers to host groundwater are present. So it basically makes, when you're looking at a large hydrologic study, it makes a large area of that basin in the proximity of the caldera probably not a likely source of groundwater or recharge. You have to look elsewhere.
Okay, Patty also wondered if you would say more about the Olympia-Wallowa lineament.
Yeah, so that's a major structure that comes southwest, or excuse me, my direction is straight, northwest to southeast into the area of Walla Walla, Washington. This is one of these major geophysical lineaments, much like the Klamath Blue Mountain lineament, that really is structurally, you see it in the Milton Freewater area as kind of a major northwest striking fault zone associated with the Yakima Fold Belt. You know, west of that, I haven't worked on it a lot and can't really give you much of the particulars of it.
Okay, Gary, I personally don't understand this question. Maybe it makes sense to Jason. What is the period of rotation for the state of Oregon if it completed a full 360-degree rotation?
I don't know.
Gary, you want to unmute and clarify if you still have that question? No.
Okay. Yeah,
We will move on.
All right.
So Bill asked, could you discuss the recent movement associated with the bulge on the west side of South Sisters?
Oh, that's not something I followed too closely, and I'm probably not the one to give that information on. But the USGS put out some press releases on that and some more information on it.
Okay, Dana asks, although dissolved in 2011, the Minerals Management Service was tasked with obtaining and storing copies of drill logs and samples from geothermal exploration of known geothermal resource areas. In the early 1980s, UNOCAL Geothermal was doing exploration, surface sampling, geophysics, and drilling in Central Oregon, focused on the Sisters area and Newberry Caldera. I don't know what became of those data. Were you aware of this resource? And if so, were you able to obtain any of these data?
I don't have that data, and I've never actually looked for it because I haven't been working in that particular area. Clark may know something more about that. Do you, Clark?
It was part of the ERA program that we did. And yes, that is part of the geothermal part of our website. All of the well logs that we have at the MLRR, Mine Land Reclamation and Regulation Office, have been scanned and available. There's also geochemical, geophysical and other data, or at least ways to get to that data, also on that part of Tagami's site. So yes, in part, we probably have some of that data, but I'm thinking that Dana, the rest of that, particularly if they're UNICAL and some of the other ones, Anadarko stuff, that stuff is somewhere else. We just may not have it.
Okay, Charlie asked, there was a recent article saying that there was a potentially large ore body for lithium at the Harney Basin or more towards California-Oregon border. Would this have anything to do with your work on the water resources?
Well, I think what you're talking about there is down in McDermott area on the northern Nevada border, which is significantly south of where we're working in the Harney Basin. We haven't moved that far south yet, and is in older rocks of the 17 to 16, 15 million year old McDermott volcanic sequence. So that doesn't really have bearing on what we're looking at as far as groundwater in the Harney Basin.
All right, Paul asks, are the dynamics of the Hood River Graben similar to other Willamette Valley pull-apart basins, such as the Tualatin and Portland basins?
Sure, I can speak to that one a little bit. Let me see if I can go back in my slideshow.
It was a good diagram of the strike slip faults.
Yeah, we can go back a
Yeah,
little
please.
bit here. Not that one. Yep. Yeah, so here is here's the Tualatin Basin associated with the Gales Creek Fault, which is one of these major structures that likely extends down through here, parallel structures to the Mount Hood Fault zone. So these are these major northwest strike slip zones. And actually, Darcy McPhee of the USGS did a nice paper on the Tualatin Basin that basically looked at it also as a transtensional pull-apart basin. But this would be in the forearc of the Cascades, not within the main part of the arc. But certainly developing within the same sort of tectonic environment, and also associated with extensive Pliocene and younger melts in the boring volcanoes that developed within that particular area and field. So yes, it shares a similar tectonic and volcanic history as what we're talking about in the Hood River Graben.
Yeah, good.
And along the same lines, Bill is asking, is the Hood River pattern of pull-apart basins mapped in Washington State north of the Columbia River?
That's a good question too. So yes, it's being worked on. So in this program of mapping, I'll go back a little bit more, if I can get there. Oops. We'll get to the map that shows the work. So the thing I didn't point out here is, so we've done all these areas in orange are basically our mapping. and out towards Biggs. The areas in blue are being mapped by the USGS, including areas just to the north of Hood River. So my mapping stopped at the Columbia River, but the USGS is working on more areas to the north as we put together a new geologic map of the entire Columbia River Gorge National Scenic Area. And there's more information up there. It's just not publicly available yet. But some of what I've done included in here north of the river, my good friend and mentor, Paul Hammond, did a lot of mapping there a long time ago. And I had my own personal access to some of that mapping to include some of those ideas. So, yep.
Let's see, Scott Burns says, Jason, 2 superb talks. What is the relationship between the eruptive center at Sylvies River Caldera and the Yellowstone hotspot? Also, what is the relationship between the Sylvies River Caldera and your Prineville Smith Rocks Caldera, which I believe you say is related to the Yellowstone hotspot?
Right. Interesting question there, and not fully one we've completely unraveled. I guess what I could say is, one of the major questions has always been, well, if these ash flow tuffs erupted in the Harney Basin or part of this Northwest Younging high lava plains trend of silicic rocks, why in the Harney Basin? Why there at Burns? What is special about that area? So in particular, relationship to the Yellowstone hotspot, well, that area occurs within a central part of where the main phase or the original early to mid-Miocene phase of eruptive activity occurred of the silicic rocks. So the Dinner Creek Tuff erupting from Castle Rock Caldera just to the east of the Harney Basin. You're in between the Steens Mountain basalts and McDermott Caldera and some of the northern Nevada stuff. So the Harney Basin is within that central area. And probably without saying too much about it, it may have something to do with proximity to Columbia River basalt dikes that possibly are in the subsurface. There's some kind of structural weakness in that particular area that's focusing that type of activity in that region. As far as the Crooked River Caldera, the Oligocene Caldera at Prineville, yeah, there was work out of the University of Oregon that related that in the area between early Yellowstone eruptions of Silesia, which formed the Coast Range, in making the connection that it connects out to later mid-Miocene eruptions out east, because it carries many of the hallmark isotopic and chemical hallmarks of Yellowstone type eruptions. And there are researchers that are continuing to delve more into the geochemical topics of that and further substantiating that interpretation. The other interesting relationship is, in the reason I put these 2 talks together is, again, as I mentioned, both really late Miocene and younger rocks. So there is an interesting research avenue to follow up on in the structural evolution of Oregon from the late Miocene on, is you get the development of what we know as the modern high Cascades around 8 million years ago or 9. And that is at the same time we're getting these eruptions out in the Harney Basin. So that's also an intriguing idea that eventually I will have time to follow up upon and see where that leads. But that is also an interesting dynamic, both structurally and magmatically, what's going on, that the Cascades are beginning to form at the same time that major eruptions out east. That's probably the best I can do on that for now.
All right. So Bill asked, excessive mining of groundwater can possibly create localized subsidence of surface elevations. Are you seeing any subsidence?
In the Harney Valley?
I believe so.
Yeah, just throughout the state, Jason, just in your travels.
Oh, well, that's an interesting question. I don't know if I have specific examples of subsidence, but certainly in areas where groundwater, I mean, certainly in the Prineville area where we worked for a long time, lots of evidence, not where there was subsidence, but people end up chasing groundwater aquifers. That is essentially going deeper and deeper as they run out of water near the surface and looking for to exploit deeper resources. And lots of times those turn out being water that either you don't want or has temperature problems or things like that. So I've seen lots of issues like that, but I can't say that in specifically, at least off the top of my head tonight, that I can think of subsidence features. But that is an interesting one to think about. But the guys at Water Resources in Salem, a few of those folks, if you're interested, I could direct you to them. They may have examples of that.
Okay, Denny asks, did the deep drilling produce cores? If so, would the cores contain new information about the strata?
So from the Harney Basin exploration wells, there was just chips and cuttings. There were not cores that I know of from that. What exists is the chips, and that's the issue with some of this stuff. Clark kind of mentioned it when he was talking about the stuff there at Central Oregon, is that it doesn't always make it. It doesn't always stay archived, or at times gets disposed of. So there could have been cores with those wells, but in the records we have, I don't think there were.
Okay, and I think just one more question from Bill. Any updates on your thinking of the Yellowstone mantle plume creating the Crooked River caldera?
Well, I mean, I just kind of went over that a little bit. I think it's still a valid idea, and there continues to be researchers at U of O and University of Geneva that have published some recent abstracts showing more chemical data on oxygen isotopes and zircon ages and things that continue to support that idea. Myself, I'm kind of getting at that by doing a broader research study of both the John Day and Clarno formations and looking at their stratigraphy, their nomenclature, and the position that those rocks hold between the Eocene silex out on the coast and the Miocene Columbia River basalt inboard. So, I keep plugging away on that, and I guess I'll have more information when I get that paper done, but that's in the works, because I think that both the Clarno and John Day in total, not just the Crooked River caldera, but they hold a lot of those keys to those answers, but they have been very, very little significant modern research that's been done on those. So I think more to come on that topic.
Okay, great, thank you. That is everything that's in the chat, and it is 9 o'clock, so I think we'll stop the recording. And if anybody has any further questions, if Jason's willing